All right, guys, welcome back into the demo video. So now you can see demo is back on the slide. But what I'm gonna do now, I'm gonna actually show you the practical implementation of the kNearestNeighbor in the PySpark that obviously you can use by yourself to address the simple, I would say, machine learning problem. And let me tell you, because you have now all these tools in your bag. So once you get the any data science or machine learning problem, evaluate it and then see which algorithm is going to perform best against the problem, and then choose that algorithm. It's not like, like I mentioned, we don't have a silver bullet for every kind of problem in the machine learning or data science space. So we need to do the analysis first, analysis phase, where we evaluate the problem and then we evaluate it against the available algorithms and see which one outperform the rest, and whatever is going to be the best algorithm for the problem, we're gonna pick it, right? And it change from case to case, right? And there is no I tell you, there's no single I would say standardization solution. The solution varies from problem to problem and industry to industry and even organization to organization, right? So always, never ever blindly follow any algorithm because it was famous in the industry. Maybe it doesn't work good well for against your problem. You need to analyze your problem and then you need to decide, okay, I'm gonna use the logistic regression, or I'm gonna use maybe the k-mean clustering, or random forest, or the kNearestNeighbor, right? All right, so let me just reshare my screen. I'm just going to now, I'm going into the dev environment. So hopefully you guys can see my screen. As usual, I'm just going to increase the size of the notebook, the visible size, because last time I remember it performed really bad in the video because the visibility was not good. So hopefully now you can see my my notebook. So obviously I have the DataBricks free cluster, community cluster, and you can see the default language is Python, because in PySpark library the kNearestNeighbor is not built. So we're gonna actually build it from the scratch, because kNearestNeighbor classify, for somehow they haven't built it. I'm not sure what they where the community is from the classification algorithm perspective. But that said, it's not going to stop us building our own version of kNearestNeighbor. And that's where the power is, because once we build any algorithm by ourselves, then we know the internal mechanics, right? It's more like you build the engine of your own car, and now you know all the internal mechanics. So once you are driving and anything is not feeling right, you can literally stop, open the bonnet, and look at the engine and all the internal structure to identify the problem, right? So that's where normally the mechanical and the driver overlap comes into the picture, right? So obviously, if someone has the mechanical knowledge of car, he's going to be not only a good driver, but as well as the good mechanical or good look after of his car, right? So same apply in machine learning. Like in machine learning, we if someone knows the internal mechanics or the internal mathematics, and any issue happen with the model, he can literally, or she can literally go deeper and find out the root cause and fix it, right? So that's our first algorithm that we have developed by ourselves, instead of using it from the library. So you can see I'm using the Numpy, which is obviously the multi-dimensional array library, which help us to prepare the data in in terms of numerical format or numerical arrays, so we can feed that data into our machine learning model. And pandas provide us the data frame of at this stage we are not using the panda, so you don't need to worry about. But just if you just want to get the idea, panda is more like, they provide the data frame which we have already used in the PySpark in the previous notebooks. And I think what I'm gonna do, once we do a real live example with kNearestNeighbor, you're gonna see the panda library is going to be used, and it's gonna actually contain the data frame data that we will convert into numerical values and then feed it into NP arrays, because NP array data is going to feed into the machine learning model. Now you can see we have the kNearestNeighbor classifier, which is getting the data set, because if you remember, I mentioned that it's going to actually take the data points, and then obviously the point is the unknown point, which is not classified, and k is representing the total number of neighbors. So based on the value of k, it's going to actually determine the closest neighbors of point p, and based on those closest neighbor, it's going to actually determine the class of the point, right? So pretty simple. Now I'm not going to come into the functioning. I'll first show you how we are going to do the data set. So, in Numpy is really powerful library, especially once we generate not only the multi-dimensional array from the data frame or data set, but also if we want to generate any sort of, test data, or if we want to, apply any existing mathematical or numerical functionality, Numpy is there, because it has already been built in Numpy, and because the functionality is there, so there's no need to to invent the wheel, because you can reuse the functions or libraries which are highly optimized from Numpy, right? So what I'm going to do, I'm just going to generate the 100 random number. And these random numbers are going to actually come come in the range of 0 to 1. So I just converted it into because after multiplying with 100, the range will obviously uplift towards 0 to 99, right? And I'm changing, because it's an array, so I'm changing the shape of the array. It's going to give me one-dimensional array. I'm changing the array to two-dimensionals, because 2 is going to be the row, at 50 is going to be the column. So what's going to happen, we're going to have the 50 by 2 row, and I'm going to actually show you in a moment. So if I just show you the type of the data set, my data set variable, which is or object, which is containing the returning multi-dimensional array. So you can see its type is ND array. So let me quickly, I think, let me quickly my data set. If I actually show it to you, so you can see we have 2 columns and we have 50 rows. Sorry, the second argument is column. Yeah, my bad. So second argument is column. The first argument is number of rows. So you can see we have 50 rows and 2 columns, right? And now similar way, I'm just going to and you can see the value range is coming between 0 to 99, right? So there's not a single value which is less than 0 or greater than 99, right? So that's how we generate the test data. Now I'm now going to do the same thing. I'm going to generate the random point. So now that's my random point. And for example, I want to classify this point. So what now I'm going to do, I'm going to call my kNearestNeighbor classifier. I'm going to pass my data set, which I have generated, which contain 50 points. I'm going to pass the point which I want to classify, and I have actually generated I have passed the number of neighbors as 3, right? So it's going to return into k neighbors an array of 3 points which are going to be closest to point P compared to other data points, right? So up to this point, we are pretty good with the problem set. Now we are going to go back into the function, and we're gonna see how the kNearestNeighbor classifier is calculating the 3 nearest data points. All right, coming back to the algorithm. By the way, that's the shortest implementation I have implemented it. Like it's a one function. Normally, just to keep things simple, we divide it into multiple functions, but that's the shortest one. And you're gonna see the efficient one, which we have built to classify any point, right? And all you need to do, just prepare your data set and convert it into multidimensional array and forward it to kNearestNeighbor, and it will, classify by that object. Now, what I'm going to do as a first thing, obviously, I want to keep the result. So I've just declared the dictionary. Now, what dictionary is, normally how the dictionary works. So dictionary always have Right. So the dictionary, how the dictionary works, dictionary is more like, it's more like a key value pair. So we have key, and then based on that key, we have some values. So for example, let me just drive a value, and these values can be any type of value. It can be a single object, or it can be multi-value object, any kind of structure we can keep against our key. And now the beauty is it's not going to store one key. Actually, it has let me just copy. It has array of multiple key value pairs. So you can see that that's gonna go all the way. So that's the whole concept of dictionary that we use, right? Now what we are going to do, we're just gonna play smart, and what we'll do, we'll keep the distance as key. And obviously, because the point, we don't know whether it's going to be two-dimensional point, three-dimensional point, or maybe n-dimensional point. So that n-dimensional point we're gonna store as a value, right? So each distance is going to reflect its corresponding point, because then what's going to happen at the end, once we extract the top 3 minimum points, those points not only give us the minimum distance, but also based on these 3 points, we can use them based on these 3 minimum distance, we can use these distances as key and extract the points from the dictionary. So that's the concept of using the dictionary. All right, now, so obviously we are going to calculate the Euclidean distance against each point into our data set, and we might have, at the moment, we might have millions of data points, right? So I'm not going to right now discuss, the dissection of the plane, and look at which one is the closest, all those optimization technique that we normally use in the research. Let's park it for time being. It's a simple, plain traversing of your data set, right? Regardless whatever it is, regardless the arrangement of the points within the data set, right? So what I'm going to do, I'm just now looping every point in the data set, and my first step is calculating the Euclidean distance. And let me just read it out for you from inner to outer, because obviously the inner is going to be executed. So you can see I'm using the Numpy library function called subtract. So what it's going to do, it's going to actually subtract 1 point from other, and the beauty is it's going to actually look after the indexing for me by itself, right? So what will happen? So for example, if we have these 2 dimensions, right? So what subtract will do? It will subtract the index 0 from the point index 0 value. So it's going to subtract. So for example, let's take 84 0.4065 comma 76.69. So if I use the subtract method of NumPy, what it will do, it will subtract the first index from the first index, which is 2 of my unknown point, and it is subtracting the index second from the second, and all the way with the n number of index, right? So you don't need to worry, you don't need to mention it. So because these are the advantages of using the built-in function of the NumPy library. All right. So obviously, like if you remember the mathematical formula, so that's going to actually give us the difference between those 2 points. And obviously, why I'm actually multiplying it with the similar value again, because we want to take the square, right? So square, once we get the square, we're going to sum up all the values, and again I'm using the sum value, and once the total sum will come up. If you remember, I told you that we're going to actually do the square root. So that's a pure Euclidean distance formula that we have discussed in the previous video. If you haven't watched the introductory video, I'm going to place the link, and you can visit back and understand the mathematical equation, right? So that will give us the Euclidean distance, and I will check. Okay, now whatever so if we start in the sequence, so initially our dictionary is empty, and the first k points, they are not going to be compared against anything, because we first need to put the k points as it is, right? And then we start comparing, okay, whatever the next k plus 1 point gonna come in, whether it has the less distance compared to this point, so we can replace this point with the existing one, right? So that's why I put that condition. If the length of the dictionary, which is going to hold my Euclidean distance and point, is less than k, if the number of dictionary keys is less than the value of k, which is obviously in this case is 3, then just add the point item, whatever point we extract, and you can see I'm actually placing the Euclidean distance as a key. So that's a syntax of the dictionary. Once you add any item in the dictionary, you provide the key in the square brackets, and you provide the value against the key value, right? So you can see in here. So that's one case. All right. So now imagine we have now 3 values that have been added into my dictionary. Now 4th value come in, and what I'm going to do now, I'm going to actually going to sort the dictionary keys in the reverse order, because what it will do, it will give me the highest distance which is sitting into my dictionary. Now, as soon as I get the highest distance, which is the highest Euclidean distance, if my max key is going to greater than or equal to that Euclidean distance, right? So what I'm going to do, I'm just going to add my point item into the Euclidean into the dictionary, and I'm just taking out that distance, because obviously that distance is greater to the upcoming distance, right? So the logic is pretty simple. Again, what we're gonna actually get the maximum distance key from our dictionary, and I'm gonna actually check against my distance. If that maximum key, which is obviously maximum Euclidean distance, is the new Euclidean distance, if it is going to greater than the new Euclidean distance, all I need to do, just add my new Euclidean distance, similar as I did in the first 3 rounds. But the only additional part which I'm going to do, just take out that key plus value from my dictionary, because obviously my new distance supersede this old maximum distance, which is obviously further than this new point, right? So that's how I'm just going to maintain the 3 nearest point into this dictionary, which are nearest to the given point, right? So at the end of the execution, once that loop finish, what I'm gonna do, what I'm gonna I'm gonna get the result, and this result is going to have three points, obviously with the distance, which are stored as a key against each point respectively, right? If we pass the 5, then we're gonna actually have the 5 points in this dictionary. So that's the simplest implementation of the kNearestNeighbor algorithm from the understanding perspective. Now, so we have already run it, and I do believe we have the data. What I'm going to do, let me just clear the cell output. All right, it's not in here. I was just mixing it with the Jupyter notebook. All right, so we'll start in here again. That should be all right. We are going to just, so that's fine. Nearest neighbor. Oh, so what's going? I think it's complaining about. Oops. So I think because, let's see now. Yeah, all good. I think. So what's the problem? Let me just increase. Hopefully it won't actually complain now. Yeah, it's all good. Yeah, all good. So yeah, it was just while I was actually increasing the zoom previously, it just disturbed the indentation, and Python is very sensitive towards the indentation. So now the next one, I'm generating the data set. So I have now 50 points, obviously with two dimension. Type is obviously multi-dimensional array, and these are the 50 data points that you can see on your screen. Now I'm just going to create a random point that I want to classify based on the kNearestNeighbor, and you can see I'm keeping it in P, and I'm just calling my kNearestNeighbor classifier, and I'm passing the data set, my data set, which contain the 50 points, the new point, and the number of neighbors, right? So let me just increase it to 5, just for the sake of understanding. All right, so once I run it, I'm going to actually receive 5 nearest neighbor, or 5 data points which are closest to point P from the my data set, right? So let me just display it for you, and you're gonna see these are the 5 points. So you can see they are displayed with their corresponding keys, right? So you can see 15.47 is the Euclidean distance, and it is actually against the point 85.7550, right? Similar, we have 17.30 distance, which is obviously coming by using 0.67, 24, and then respectively we have another 3. Now obviously in the machine learning there are many points. If you want to draw anything, it would be harder to understand how things work, right? So what we're gonna do now, we're gonna actually draw the all the points, and we're gonna see whether our chart or graph portray the similar concept that we have discussed or that we have created or developed, right? Because that will be an additional confirmation if we can look at the chart, and if we can see the points which we have received from our algorithm are closer to compared to the other points, right? So just for the clarity perspective, the actual points in the data set, I have actually shown them in blue. My new point or the candidate point, I'm showing it with green, and obviously all the nearest neighbor which I got from the algorithm, I'm showing them with red, right? So now let's run it, and now there we go. You can see that's these are all the points which you can see are scattered on the two-dimensional plane. And then obviously I have my green point in here. Now pay very close attention. All these 5 points which I received from my algorithm, these are the closest points to to my candidate point, which is represented in green, right? So you can see this point is further, this point is further. The only doubt we can have on this point, but if we can pay a very close attention, we're gonna see this point, this red point is closer compared to this point. So that's another proof that our kNearest classifier is working great in the PySpark, and our algorithm is working fine, right? So obviously, as soon as we increase the number of points, the visibility is gonna be harder. So let me just, what I'm going to do 10,000, and I'm going to, because these random values are going to be two-dimensional. So let me just, change it to 5,000, and let's see. Now I'm going to just do it again, but you will see now the visibility is going to be harder, right? So let me just show it to you. Oh, wow, you can see it. And you know what I'm going to do? Let me just do, because S shows the solidity or the weight of the point. So let's see now where we're gonna have it. So you can see there's so many small points, and underneath, between these points, we have somewhere our point. And let me just take this one to also small. So at least our green point is visible. Yeah, so you can see our green point is visible, and the red points are overlapping our green point, because our green size is quite high. So let me just, yeah, decrease the size. So now you can see, yeah, it's still better to realize, right? So now imagine that that's just the 5,000 point. What about if we have 50,000 or even 500,000 or even 5 million points, right? So you can imagine how dense is this graph is going to be, and one thing I can do, let me see if I, just for this, just to show you the efficiency. So that is, let's say, 100,000 and 1 million and 10 million, right? Yeah. So what we are going to do now. Yeah. All right. So let me just show you. So we have generated almost 5 million points. Yeah, 10 million, we have generated 5 million points, right? And based on the 5 million points, we're going to actually determine the value. I'm going to keep the the k value as 5, right? Our array is going to be quite big, right? So and then we have our point, which is obviously again with 2 dimension. And now let's run it. Because remember, this time it's not running against a small data set. We have the 5 million points, which we are actually running against, and we're going to see how the algorithm perform. And I will see once we have a next version of the kNearestNeighbor, I'll put the timing so we can see. Anyway, it's going to actually show us the execution time in the status bar, so we don't need it, because normally in Jupyter notebooks we can put the timing. So while it's running, we can get unit 10, 100, 1,000, 10,000. Yeah, we have 5 million points. So you can see it has been executed less than 54 less than 1 second, which is not bad, right? Even we can improve it. Like I mentioned, at the moment I'm just treating the data set as it is, but we can improve the efficiency without any additional effort. So now let me run, and we can see the points are now coming with their distance. And let me dare to draw the scatter plot. I do believe so. You see, it's gonna actually take a lot of time to draw. Wow! So you can see we have a complete blue rectangle, look like a blue rectangle, and underneath you can see a very small, very small red dot, because green we cannot see because these points are so close to each other, it's hard to visible. But that's how the kNearestNeighbor works. It's not available in the PySpark library in the classification, but we have the full opportunity, so we can build it ourselves. So we're going to also see a practical example where we're going to actually classify an object using the same algorithm which we have discussed. So hopefully it will benefit you and help you to understand the k-nearest neighbor, not from the theory perspective, but also from the demo perspective. I'm going to actually upload this notebook on my Git. If you want, you can go and download it, and you can use the function by yourself anywhere you want to. And please put any comment or question if you have. Otherwise, like the video, and I'm gonna see you in the next one. Thanks for watching.